Right, so the specific heat capacity practical then. So in this practical, what we're trying to do is we're trying to heat up some blocks of material, some cylinders of material, and we're going to see how much energy it takes to heat them up by, or raise the temperature of the blocks by a certain amount of degrees Celsius. So what is specific heat capacity then? So specific heat capacity is the amount of energy it takes to heat 1 kilogram of a substance by 1 Kelvin or 1 degree C. In this practical, we've got 3 blocks. On the left, we've got a copper block. In the middle, we've got an aluminium block, and on the right, we've got an iron block. The setup looks incredibly complicated. Actually, in class, it's more likely that you only did one at a time. So it would have been a little bit more simple in class. But for the sake of time and for the sake of convenience, I'm just going to do all 3 blocks at the same time, side by side. So I've set 2 of them up, ready, and you're going to see me set up the 3rd block. So having a look around at all my kit then. So I've got the data loggers. That's me picking up the. That was the immersion heater that we're going to put inside. Now, right now, I'm just wiring up the heater. I'm going to put the heater in series with an ammeter. So I'm going to allow. I'm going to put it in series with an ammeter so that I can measure the current through it. And I'm also, in a moment, once I've set this up, I will be putting a voltmeter in parallel with it. The reason I want to do that is because I need to be measuring the amount of energy that's going into the block. So in order to do that, I will take a measurement of power. If you remember from your electricity lessons, electrical power, that's the energy that that's the power that we're going to be putting into the immersion heater. Electrical power is current times voltage. So we just take those 2 and multiply them. Right, so it's a bit weird. Look at what I'm doing. I'm putting some water in the holes. Now, the whole reason why I'm doing that is so that I can get a better thermal connection with the block. I'm going to fill the right-hand one up. That's the one for the thermometer. I'm going to fill that all the way to the top because I'm going to be using a thermometer that doesn't quite touch the sides. So I'm going to be using that water, just going to provide a better thermal connection with the block, allow more heat to be transferred into the block more efficiently, and likewise it will allow the temperature probe to measure more effectively as well. So I've got the data logger set up. All I'm going to do is I'm going to turn on the power supplies first, dial up. I'm going to try and dial up 12 volts on each one. So get to 12 volts on each one, and then I'll be measuring the current as well, and I'll be recording the current. And then later on in the follow-up video, we will figure out the power, and then we'll go through how to figure out how much energy has been transferred into the block as well. So I'll just speed it up to the point where I'm going to start taking some measurements. Actually, before we take measurements, I will just show you the circuit diagram. So I've got the power supply in series with an ammeter and the immersion block there. I'm not entirely sure what the circuit symbol is for an immersion heater, but that's what I'm just going to put it there. Now I'm going to put a voltmeter in parallel with it. That's not a particularly well drawn voltmeter, and then there's the block there. So it's not the best circuit diagram in the world, but it gets the point across. Ammeter in series because that's which is where you put an ammeter, and a voltmeter in parallel because, again, that's just where you put a voltmeter. Voltmeters need to go in parallel because they don't conduct electricity. It will stop the electricity flowing through the flowing to the immersion heater. Right, so I've set up the camera. So there we go. I've just started taking a reading. Now I'll just take some zero readings, some readings at t equals 0, time 0, and then we'll let it run. I'll put the table. I'll just fill in the results for the table as time goes on. I'll speed it up so it's nice and quick. I'm going to take 10 minutes worth of readings, so you don't really want to be sitting here for 10 minutes just watching this. So for the sake of convenience, I will speed this up. It's a little bit easier to do that than obviously when you're in class. You can't just speed up time. But I can do that with the magic of video editing, so we'll do that. So you should be noticing as time goes on the temperature is increasing, of course. Now, some of the temperature is increasing more for some than it is for others. I forgot to mention as well, the red reading on the screen, that's the one on the very far left, that's the copper. The blue reading, that's the one in the middle, that would be the aluminium. And the green reading, that's the one on the right, that's the iron. They're all 1 kilogram blocks, by the way. I don't think I mentioned that either. So they all have a mass of 1 kilogram. They're different sizes, but that's only because they're different densities. So their actual volumes are different because they're different densities, but they've been machined to have exactly 1 kilogram of material on them. So whilst this is running then, we'll talk a little bit more about specific heat capacity. Specific heat capacity is the amount of energy is required to heat up a specific material by 1 degree C, 1 kilogram of that material by 1 degree C as well. And it's specific to the material. So aluminium will have a specific heat capacity specific to aluminium. Iron will have one specific to iron. Copper will have one specific to copper. Water has one. Any material has got a specific heat capacity because you can heat it up, and how much energy does it take to warm it up by 1 degree? Well, that's the energy, that's the specific heat capacity. Right, so let's keep going, let's keep recording. Now, right, so coming up to the final reading then, so the last one, I'll do something really stupid here as well. So the copper block is the hottest at the minute, so that would imply that it's risen by but despite having roughly the same amount of energy put into it, it's risen by more. Its temperature's gone up by more, and 80 degrees, and I'm just testing it to see, how hot it actually is, to see if it actually is 80 degrees. Terrible idea, by the way. Never do that because you burn your hand. That was not pleasant. Right, so what I'll do then is I'll see you in the, I'll get the results together and I'll see you in the follow-up video.